Hello, my name is Anna Bunger, and this is Lab 3, Black Hole, for Physics 2211 at Georgia Tech. There are two parts to this lab. In the first part, the mass of a black hole is calculated by analyzing its orbiting star's motion. In the second part, the motion of an orbiting spaceship is calculated in a given problem using the black hole's mass calculated in Part 1. Here are the fundamental principles involved in this lab. Newton's second law states that the net force of an object is equal to the object's mass times its acceleration. This is also known as the momentum principle, which states that the object's change in momentum over a given time frame is equal to its net force multiplied by that change in time. The position and velocity update formulas can be derived from the momentum principle. The position update formula states that the final position is equal to the initial position plus the average velocity times the change in time. The velocity update formula states that the final velocity is equal to the initial velocity plus the net force divided by mass over the change in time. The net force of an object can be broken into its parallel and perpendicular components. These are equal to the derivative of momentum over time. Through the product rule, these components are as stated. The perpendicular component is responsible for the object's change in direction, and the parallel component is responsible for the object's change in speed. It should also be noted that the net force of the object is equal to the gravitational force in this problem. For Part 1, these are the initial conditions. The star is orbiting around the black hole counterclockwise. Its mass is 2 times 10 to the 30th kilograms, and the time step is equal to 1 day, or 3,600 seconds. The system in this problem is the star, which is seen in the picture as the yellow circle, and the surroundings are the black hole in space. Here is the code used in Part 1 of this experiment. Lines 10 through 11 show the seed used to generate position data, which is unique to each student. Lines 118 to 128 show the initial conditions stated in the last slide, and lines 159 through 194 show how the forces were calculated. Here are the results from Part 1. The mass of the black hole was 3.53 times 10 to the 36 kilogram, and the possible sources of error come from Python rounding approximations. Shown here is the star's orbit and net force. The parallel component, shown by the red arrow, is tangential to the orbit, and the perpendicular component is perpendicular to the parallel component and always pointing towards the black hole. Part 2. The initial conditions are as following. The mass of the planet is 9 times 10 to the 28th kilograms. The mass of the black hole is 3.53 times 10 to the 36th kilograms, and the mass of the ship is 7 times 10 to the 10th kilograms. The direction is in the positive y-axis. The system for this problem is the spaceship, and the surroundings are the black hole and the planet. Here is the code used in Part 2. It should be noted that in the initial conditions, the mass of the black hole is the same as calculated in Part 1. The initial velocity was the vector negative 1.45 times 10 to the 7th, 1.45 times 10 to the 7th, 0 meters per second. This was found through trial and error using the position update formula. The closest distance between the spaceship and the black hole was 4.93 times 10 to the 9th meters. The possible sources of error come from approximation errors. While the net force and the rate of change of momentum are the same numerical values, when broken into their parallel and perpendicular components, they differ. This is because the rate of change momentum is calculated through position, time, and velocity, whereas the net force needs the object's mass to be calculated. Part 2. I am not sure of the exact calculations, but I would predict that the initial velocity would need to be less than the spaceship's escape speed. This is the minimum speed needed for an object to break free of the gravitational pull of another heavier object.